Hello, it's August 5th, 2012. I'm Joe Delaney, a physics teacher at South High in Minneapolis, and today I'm going to demonstrate projectile motion using a stream of water. And the special contribution I'm going to make is how to find the initial velocity. I'm going to use two methods, and both of them based on this water. First method is a volumetric technique, and I'm going to capture the water at a measured rate, so many cubic centimeters per second, and after I find how many cubic centimeters per second, the collection rate, if I have the cross-sectional area of the tube, I will simply divide that cubic centimeters per second by this number of square centimeters the cross-sectional area. That division will give me centimeters per second. It'll give me the speed of the water coming out of the tube. So that's the first method I'm going to demonstrate. Now, I have a reservoir here, and which you can't see that it's constantly overflowing, just a little overflow. I drilled a hole that you can't see in the other side near the top of that reservoir. And I have a supply from the hose that's going in there just a little bit more than the rate at which I'm losing water from that in that projectile motion. So that's how I'm keeping the pressure head the same for the difference between the top of that reservoir and the opening of that tube. So I think the biggest challenge is to find the cross-sectional area of that tube, and this is the method that I provide. First, I have a wonderful electronic balance. Get the tube dry, and I'll weigh that, I'll tare that, so that's zero with the cup and the glass tube in there. I take it out, I dump it in this vat of water here, and shake it around until the bubbles come out of it. And you can see the bubbles in a glass tube. That's a nice thing about that. If there's any bubbles, you can see them. And after I've got the bubbles out, okay, I take that glass tube out between my middle finger and my thumb. I've captured that water, and I would dry my hands and the outside of this tube, because that's the water I don't want to be measuring. And I don't have my napkin. Oh, here we go. So I simply dry the outside of that tube and my hand a little bit so I don't drip on the scale. I had to do this inside because even a little wind out here would make the weight go back and forth a little. So I empty the tube into that cup and reweigh it. When I did this, I got 1.80 grams, which translates very nicely to 1.80 cubic centimeters, because the density of water is very close to 1 gram per cc. The next thing I need is, I still don't have the cross-sectional area, I have the volume, but I measure the length of this glass tube. This is a very cheap vernier caliper I got at Northern Tool. It's kind of nice because it'll measure up to 15 centimeters in length. When I measured that, I got 13.2 for the length of the glass tube. Dividing that 1.8 by 13.2, I get 0.136 square centimeters. So voila, there is the thing I need, the cross-sectional area. when I did this collection, I had my stopwatch ready and ready to collect. As soon as I moved in, I hit that stopwatch, went for like 10 or 20 seconds, hit it again when I pulled it out. I did that a couple of times. And of course, again, this is a wonderful digital scale because it goes up to 2,000 grams. So I put that on there. Of course, was taired and all that before I did that. I found the weight of that and timed that twice. The first time I did it, I got 302 cubic centimeters in a time of 13.4 seconds. The second time I had 471 cubic centimeters in 20.2 seconds. That gave me a collection rate, 22.5 cubic centimeters per second, 23.3 cubic centimeters per second. When I divided that by that cross-sectional area of 0.136, I got two values for the speed. 166 centimeters per second, 171 centimeters per second, and with an average of 169 centimeters per second. So that's one way of finding the initial velocity. I want to use another way, energy method. You might like this better. Nice and short and sweet. And I think the kids would, some of them might have trouble with the volume method. This method, the second method, is energy, conservation of energy. I'm going to take that tube and change its orientation, but not the height of the tube, so it'll still be the same pressure head to the end of that tube. And when I aim it straight up, starting out, I'll set the potential energy level at the muzzle as 0 joules, and then as it shoots up, it's all kinetic energy then at the bottom, 0 potential, and at the top the kinetic energy is gone, it's been turned into potential. So the difference between those two energies, they are equal. The difference is 0. 1/2 mv squared at the bottom equals mgh at the top. The mass cancels. I solve for v, conveniently, it's just the square root of 2gh. I use g as 980 centimeters per second squared, which is close. It's probably Minneapolis. I think it's more like 981 centimeters per second squared. But on this block of wood, I've got a split vinyl tubing. That is holding it right now to that block of wood, my 30-degree angle block of wood. And I've got another split vinyl tubing on the vertical face. So that'll be convenient for replacing that tube in a vertical position. I went like this. Measure the height. Still have 75 centimeters. 75 centimeters that way. And I have some rubber bands on there too that if I needed to hold better. Tube, so that it's at the 75 centimeter mark again. And then I measure, going to decide just how high does that water rise. One time I got 15, another time I got 16 centimeters. So 15 or 16 centimeters. When I use those values, just plugging them into the square root of 2GH, I get at 16 centimeters, 177 centimeters per second, and at 15 centimeters, 171 centimeters per second. Difference in there is 3, therefore, or excuse me, is 6. The average then would be 174 centimeters per second. Now that compares pretty close with the other method where I got 169 centimeters per second. So after that, I have a number of these blocks at different angles. I like 37 degrees and 45 degrees, 53 degrees. So the students can set those up. I have 6 reservoirs. So I can have 6 setups, 6 groups of students working at a time. It can be messy, and actually that's one of the attractive parts as far as the students go. So that's it. Thank you. I hope this helps with projectile motion.